we have a square t over 2 plus a square over 4 e raised to the power j 2 theta I, and inside the integral 0 to t e raised to the power j 4 pi fct dt, this one. And there is another part which is a square over 4 e raised to the power minus j 2 theta I. I'm just rewriting it to solve it further. E raised to the power minus j 4 pi fct dt. So these are integral we have. Now we can see that it is a square t over 2. Then from here I would have a square 4 e raised to the power j 2 theta I, and the integral of this is e raised to the power j 4 pi fct over j 4 pi fct, and the limits are 0 to t, right? Now we can solve the other one. We have another third term as well, a square over 4 for minus j 2 theta I, and from the integral we can say e raised to the power minus j 4 pi fct over minus j 4 pi fct. The limit is from 0 to t. So we have these three terms. From the first term we have a square t over t, a square t over 4, a square t over 4 plus a square over 4 is for j 2 theta I, and we have in the denominator we have j 4 pi fct as well. And let me apply this limit. So when we apply this limit, it would be e raised to the power j 4 pi fc upper limit minus the lower limit is 0, it would make it 0, right? Now move to the other one, the third term, and the third term we have a square over 4. There is another term in the denominator minus j 4 pi fct and e raised to the power minus j 2 theta I, and we apply the limit. Limit is e raised to the power minus j 4 pi fc capital T minus e raised to the power c. Now what do we get? From here you can see that it is a square t over 4 plus this term, this one. I'm just writing it. Let me give it some name. Let me give it the name A. This A term. This is A term, and then I have this one. So what is this? FC and T cancel. FC frequency 1 over time interval. So FC is equal to keep in mind your Fc is equal to 1 over capital T. So this cancels out. Similarly, this cancels out. So you have e raised to power j 4 pi. E raised to power j 4 pi is equal to 1. How? How e raised to power j 4 pi is equal to 1? So you have e raised to the power j 4 pi, which by Euler identity is cos. Let me write it here. You get e raised to power j 4 pi, and then e raised to power 0 is 1, right? Okay, I'll not write it here. Let me erase this. We will do it later. Now, in the second, from the other integral, let me say this is my c term, b term, sorry, b. So from the third term we have b times this one. Again, f, c and t would cancel. So you would have e raised to power minus j 4 pi. Then you have minus 1 from here. So this is the integration. A square t over 4 a square t over 2. I guess this was 2, this was not 4. This is a square t over 2. And here e raised to power j pi, if you see e raised to power j pi, it is plus a times e raised to power j pi. J pi is 1 minus 1. E raised to power j 4 pi. E raised to power j 4 pi is 1. Similarly, b times 1 minus 1. So e raised to power j 4 pi is cos 4 pi plus j sin 4 pi. Euler identity. Similarly, e raised to power minus j 4 pi is equal to cos of 4 pi. Cos 4 pi minus j sin 4 pi. Right? So this is 1. This one is 0. This is 1. This one is 0. So you get 1 here, you get 1 here. If you see your integral, your integral is actually equal to a square t over 2. So this is the average energy of your QPSK symbol, a square t over 2. Well, we got this energy. It depends upon the A, which is the A is the amplitude of the carrier. T is the period of the carrier. So the energy depends on the amplitude and the period of the carrier, or how long the symbol has to be transmitted. Of course, it has the effect on the energy. You can also write your QPSK symbol, because QPSK symbol is two-dimensional signal. So you can also write it as SI1 psi1 of t plus SI2 psi2 of t, right? And if you integrate it from here, which we have done earlier while discussing the QPSK, if you integrate it from here, if you integrate this symbol of 0 to t, you would get SI1 square SI2 square. So the energy, if you get from this expression, you get this one. It means Yet your A square T over 2 is actually equal to SI1 square plus SI2 square. Right? So this is the energy of your signal. Average energy is equal to this. And if because if SI1 is QPSK, so the magnitudes of SI1 and SI2, if we say that these two are, the magnitudes are same, then we can write that SI1 square plus SI2 square would be equal to 2 times SI1 square, which is the same as 2 times SI2 square, right? And if this is the case, then we can write our expression A square T over 2 is equal to 2 times SI1 square or SI2 square, it's up to you. So you can see that your SI1 square is equal to A square T over 4. Or you can say that your SI1 is actually equal to plus minus A square T over 4, which is plus minus to the root T. So you can have this value for SI. Now, if we can take this one or this one, right? So anyone is okay. So we can have this SI1 in terms of A. SI1 in terms of A. Now if you assume further, now this is the case when SI1 and SI2 are equal, right? If you further let me bring that one here. If you assume, in this expression, if A square T is equal to multiple of 4, right? So suppose it is equal to 8. Then what would be our SI1? Our SI1 would be equal to plus minus square root 2. Right? Or instead of taking it equal to 4, let me take it equal to instead of taking it equal to 8, let me take it equal to 4, which is the typical case. Suppose A square T is equal to 4. So what is SI1? SI1 would be equal to plus minus 1. Similarly, because SI1 and SI2, we said that both are equal, so we can write that SI2, which is equal to SI1, can be equal to plus minus 1. And you will see in your simulation model that for QPSK, these 4 points, which are the QPSK points, are actually, these are the coordinates. S11, similarly you have 1 and minus 1, and here you have minus 1 and minus 1, and you have minus 1 and plus 1. So these are the 4 QPSK signal points. 4 QPSK signal points, SI1 and SI2. Now if these are the 4 signal points and you are familiar with your identity, you are familiar that the energy we just said above, that the energy of the signal can also be computed as SI1 square plus SI2 square. So this would be 1 square plus 1 square, and you will have 2. The average energy of QPSK is 2, and this 2, if you observe here, this, we said that this is actually under root. We can verify it because this is 1. So if you use Pythagoras theorem, you will get 2 here. This distance would be equal to under root this one, under root 2, right? And if you see here, this is the energy of your signal. That is why we said that this is actually the energy of our signal. This is actually square root of E. And what is this? This is square root of E cos of theta I. So we have the base, we can say the base is now keeping in mind that Pythagoras theorem, which is very important, you will see it again and again. Your base, your SI1 is square root of E cos of theta I. Theta I is, we have square root of 2 cos theta I. Theta I is pi by 4. So when theta is pi by 4, we actually have 1 over under root 2, and you will get 1. So your SI1 is 1. Similarly, you can verify that your SI2 is also equal to 1, and this length, this is actually the energy of your signal point, QPSK signal point. So this is how we try to verify the signal energy. We actually started from the fact that we want to find the energy of our signal, QPSK signal. So we found the average energy of the QPSK signal, and we also showed here that the energy can be computed from the expressions, as well as from the constellation diagram. You can, if the constellation points are given, you can easily find the energy. Similarly, we also saw that we can find the Euclidean distance between the adjacent points. So I would like you to find out the Euclidean distance of these points, signal points, which you see in the signal constellation. There is another question in the exercise, which is to verify proof 3.23, and I guess we did it in the previous lecture somewhere when I was discussing, because 3.23 is the equation for QPSK, and we just with this example, if you see the equation 3.23, so equation 3.23 has to be proved, right? And 3.23 says that your SI1 is actually the image of the signal S, the image of QPSK signal over, so it is equal to this dot product. So dot product of the QPSK signal and the basis function, the first basis function, orthonormal basis function. And your SI2 is the QPSK signal over the second basis function. So I guess it's easier to find out. I don't think it is too difficult. If you take your equation, you can easily verify this. Just take your equation SI of t. You take your equation SI of t, which for QPSK is A cos of 2 pi FCT plus theta I, right? This is the same. This is same as A cos theta I cos 2 pi FCT plus A, no, actually not plus, you should have minus, because cos alpha plus beta has a minus sign, minus A sin theta I sine of 2 pi FCT, right? So this is if you write your equation in this form and then you multiply it with the side 1 of t. If you multiply this one with psi 1 of t, this is your SI of t. SI of t. Now you can multiply it with psi 1 of t and integrate it. So if you multiply this equation SI of t with psi 1 of t and integrate, what would you get? You would get SI1. So SI1 is this whole equation multiplied with psi 1 of t, and psi 1 of t is actually equal to, should be familiar with the psi 1 of t. You can see this A cos theta I cos 2 pi FCT, 2 pi FCT multiplied by psi 1 of t dt minus A sin theta I sine of 2 pi FCT to psi 1 of dt. So you can, of course, these limits are from 0 to t. So when you try this one, let me try one for you, and then we will see, because we already found the energies of the signal. So let me try this, just the first one. I'll leave the second to you people. So if we try to find out this one, what do we get? I'll just solve this integral, right? Just solving this integral. So I'll leave this second part for you people, this one. So let me solve the upper part, this one, right? First integral. Suppose this is my I1. So I1 is actually equal to 0 to t and A cos theta I cos 2 pi f ct, and psi 1 of t is 2 over t under root 2 over t cos 2 pi f ct, right? And then we have dt. So this is the first, this is I1. Now we can see that we can write this outside the integral and this one as well. So we will have a cos theta I under root 2 over capital T. Capital T is fixed, right? It's just like treated as a constant, 0 to capital T. And you have inside cos square 2 pi f ct dt, right? Now what we would get now, let's try to solve this one. So we have a cos theta I under root 2 over t, 0 to capital T, 1 plus cos 4 pi f ct over 2. And I change this cos square theta using the trigonometric identity, and we can write it a cos theta I square root 2 over t, and from this first integral you will get t over 2, right? And from the second integral you will get 0. Try to solve it, you will get these values. Now what do you get? This is a cos theta I, and you have under root 2 over t multiplied with t over 2. What is that? You get a at over 2 t over 2 cos theta. This is what we get, a of course a at over 2 cos theta, at over 2 cos theta. Now what is this at over 2? Not at over 2. This should be this. We should have this thing, a times square root t over 2. Should be a times square root t over 2, because you can see this here we have under root t over 2 and this is t over 2. So just under root t, we can just write it and write it separately here, 2 over t multiplied by under root t under root t under root 2 under root 2. And just return this one, right? And just return this one as this one. So this 2 cancel with this 2, this t cancel with this t, so we are left with under root t over 2. We are left with under root 2 t over 2. Now if you observe this, we have a under root t over 2 cos theta I. And what is this? A under root t over 2. We just verified this in the above equation. If you see here, the above equation, when we found the energy of the symbol, we said that the energy of the symbol is a square t over 2. If you see the energy of the symbol, where did we find? We said that the energy of the symbol is a square t over 2. This one. You see this? We found this energy earlier. We said that the energy of the symbol is a square t over 2. Now here we have, if you go back to that step, just let me bring that step back. If you go back to that step, our last step, we actually have the energy of our symbol. What is this? This is the, now if your energy is equal to a square t over 2, the square root of energy is equal to a under root t over 2. And here we have the square root of energy cos theta. So this is the square root of your energy. And this is what we wanted to prove, right? We wanted to prove that our S sub I1 is actually equal to the square root of the energy cos theta. Similarly, we can verify that Si2 is equal to square root of the energy sin theta. We can verify this. Now you can see why I left the other integral. I just solved one integral, I1. If you observe here, I did not solve the second integral. The reason is this here. You have a sine wave and you have a cosine wave, and when you see, you will get sine and cosine are orthogonal, the same frequency. When they are orthogonal over a period, their integral will give you this. Will give you 0. This will give you 0. That is why I did not solve this one. And but when you try to find out Si2, when you try to find out S sub I2, then you will see that part actually in the second integral would give you this one. The first integral would be 0, and the second integral would give you this value. So I leave it to you. Just try this one by yourself.